Hello, everybody. My name is Aaron Stannard, and I'm the founder and CEO here at Petabridge. And today we're making a video that I promised on social media a couple of weeks ago, but I ended up not being able to finish the recording, and I had to leave for a business trip. So this is my makeup for that now. Today we're going to be talking about how to diagnose and fix memory leaks in .NET. And we're going to go ahead and use some JetBrains tools for this, namely dotMemory, and maybe to some extent Writer, but we're mostly dotMemory is what we're going to use for this. Now let's go ahead and dive into the issue. Now, memory leaks are not a thing of the past, even though, managed languages like C# and Java have been around for 3 decades at this point. Memory leaks can still happen if we end up what's called rooting over an object. So an object that should be disposed still has a reference retained to it by somewhere else inside the application. So this is a bug that a user reported a couple of weeks ago on Akka.Persistent SQL, which is one of the plugins we ship with Akka.net. And this is a graph that he depicted showing the available memory. And so available memory is going down over time pretty steadily. This is one of those charts that kind of clearly depicts, a memory leak if you really look at the fine-grained details here. So that's that. And if we go ahead and take a look at some of his data, this user, Luca, notices a couple of things that are weird. The first is that he notices that there is a whole bunch of tasks being retained. Now, if you're a .NET programmer and you've been working with the task and parallelism library for a number of years, you know that tasks are meant to be temporary objects. They represent typically a bounded request that has a cancellation token, and if that cancellation token gets invoked, the task should error out and disappear. Likewise, if the task completes, it should disappear. So the fact that there's a whole bunch of tasks that are still being retained, sitting around in memory, is pretty suspicious. This indicates to me very clearly that there is probably a memory leak happening. This is something that smells funny, and therefore we probably need to go and investigate more. And just with a little bit of Akka.net knowledge, this future actor ref right here, this is also a temporary object that has a very similarly scoped lifespan, just like a task does. So this all looks very suspicious. So if we dive into the rest of his issue, Luca does the exact right thing that you're supposed to do with open source projects when you find an issue, which is he notes down the version that he originally deployed, the version he upgraded to, and takes a look at the releases that we published on this repository and takes a look for a pull request that might explain where this issue came from. And lo and behold, he identifies our query throttler plugin right here. Now, we have a video that I think we did a few years ago on how we use query throttling to allow a large number of concurrent requests against SQL Server. This basically is a way of limiting the number of open connections at any given time. Thus, this kind of reduces lock contention on SQL Server. That's what we were trying to implement on this pull request. But this plugin is modeled slightly differently than the one we originally implemented it on. And Luca's theory is that we ultimately introduced a memory leak in this pull request right here. So what we're going to do next is we're going to try to use dotMemory to go ahead and profile our application and see if we can reproduce Luca's findings. And after we do that, we're going to see if we can get to the bottom of what might be causing this particular memory leak. All right, so we're going to use dotMemory to try to profile the application and see what's going on here. Now, dotMemory is part of JetBrains', I think it's their what's the name of their subscription they sell here? Let me pull that up real quick. Ultimate subscription. There we go. I basically buy one of these for every member of our team at our company. So this is definitely not a sponsored video. I pay for this. I'm a paying customer. I just happen to like their tools a lot. So we're going to end up using this. There's a 30-day free trial if you want to try it. And I have a little reproduction sample that reproduces the memory leak right here, where this was based, by the way, off of Luca's description in that GitHub issue. All we have to do to produce the memory leak is connect to Akka.Persistent SQL with SQL Server. It doesn't actually matter what database you use. And we need to start a persistence query that basically runs in perpetuity. So this is one of these perpetual Akka.Persistence queries we can use for tailing new events that are being written to the database. We just need to do that, and it doesn't matter if there's any data or not. We will see a very gradual memory leak occur. And the reason why it's gradual is these objects aren't very big. So it might take a long period of time for this to become a big factor. So in Luca's case, I think it took them a month to go ahead and notice that maybe they had a problem in the background here. Now, it won't take us a month because thanks to Luca's hard work, we already know what we're looking for. So if I go and click down here on dotMemory, let me go back to our actual profiling. So our profiler is still running, and I'll show you how to launch this in just a second. But I have a snapshot, a memory snapshot I took right when the application launched, another snapshot I took maybe 5 minutes ago, and I'll get a third snapshot right now. Now, the thing to look at is not the memory total. This refers to the amount of memory that's been paged to the process. That's typically going to be more memory than what the application is actually using. And that might also include things like native memory. If the ADO.NET driver, the Akka.persistent SQL is using, is querying SQL Server, that might show up on here. But this is not the measure we care about. The measures we want to look at are the .NET total, which you can see that value is steadily increasing. But the real story that's being told here is the number of live objects. In a system where there's not a huge amount of activity happening, you'd expect this value to be pretty stable. The fact that it's steadily increasing tells us that maybe there is a memory leak here. So one thing we can do here is add these two snapshots to a comparison. And you can see down here that we've got about 426 kilobits. Actually, you can't see it because my image is over there. But basically, we have a whole bunch of about 425 kilobits of additional objects that are still alive. Now, if we go and we take a look at the memory allocations between these two snapshots here, we can try to filter these. Let's go ahead and filter it by task. Okay, let's take a look at task. Query start granted. Okay, and this will be important a little bit later. We can basically see the call chain that results in these things being allocated. I think the first thing I'll want to take a real look at actually is let's take a look at the number of live tasks in the first snapshot we took. Let's filter this down, task. Task, query grant started, 31. And we also see 31 task completion sources. So these two are directly correlated to each other. It means both of these are probably rooted by the same object. All right, so that's that for the first snapshot. Now, if we take a look at the second snapshot here, well, technically it's the third one, but who's counting? If we go ahead and take a look at this snapshot here, we can see that now instead of 31, we're up to about 1,600 snapshots. So, 1,600 tasks that are still, basically retained in memory, even though ostensibly they've completed. So this would seem to indicate that we have a memory leak. It's very slow going, so the amount of memory isn't shooting up by a huge amount. But gradually, this is going to become a pretty noticeable problem the longer the application stays up. Now, if we go back to our comparison between objects, we can see that call chain that we were looking at. Let's go and pull that up real quick. And it was, let's see, task. Let's see, we wanted to find task query start granted. Here we go. Okay, where does this come from? This comes from an Akka.NET ask operation, and that gets kicked off from the base byte array journal DAO. So we know a little bit about how ask works, that it implements a one-time single-use actor that wraps around a task completion source, and the output of the task operation is the task of the return type. So let's take a look real quick at the code that we introduced in that problematic pull request the user identified and see if we can spot what the issue might be. Okay, so rather than dive into an IDE, we're going to take a look at the pull request on GitHub because it's a little bit easier to see what was introduced this way. So right here, we can go ahead and see if we go down to, oh, you know what? Why don't we just take a look at the files changed? And let's look at one of those files that was identified by dotMemory. Let's see, this would be the base byte read array journal DAO, whatever that means. Here we go. We can see that here. If we scroll down a little bit further, here we go. This looks like what we're after right here. Here's the query start granted, and this is a little ask operation that's occurring here. So if we take a look at dotMemory again, we can see this whole call chain right here and this futures.ask operation. So I just mentioned a few minutes ago that one of the ways in which the ask operation works is we create a single one-time use actor. If I go back to our snapshot here and we take a look at, why don't we go ahead and just take a look at the total number of objects by how frequently they occur. Get a load of these three right here. We can see that there is 1,600 future actor Fs, 1,600 tasks, 1,600 task completion sources, and we can also see that there's roughly 1,600 child actor paths, which, by the way, also a future actor F also gets one of those. It sure looks like these temporary one-time use actors, which we know spawn both of these types here, these are not dying. Now, why might that be? what can we discern from that call chain we were looking at earlier? Well, I think the important detail we need to take a look at here is, where does this temporary one-time actor get used other than this await statement right here? Well, as it turns out, this pull request also introduced an actor, the actor that's responsible for processing the query start granted and return query start, request query start, and all that jazz. And we scroll down here, we can see that actor right here, this query throttler. Now, this query throttler actor maintains a linked list of actor references, but it also uses an important Akka.NET feature here called context.watch. This is a feature that's used to keep track of an actor that terminates basically at some point during its lifespan. So an actor in Akka.NET will normally only terminate when it's explicitly told to shut down, either by its parent or by its own code, usually. So the reason why we do a context.watch here inside this actor is so that in the event that an actor who's waiting on a token from our throttler dies before it gets a chance to receive that token or gets a chance to return it, we want to make sure we restore our count back to normal. Otherwise, you end up with kind of an algorithmic problem with doing your token bucket throttling, which is what we're doing here, where you end up gradually losing tokens to failures over a period of time, and the system will eventually no longer work if you do that. This context.watch is designed to prevent that from happening. But there's one very interesting little detail with the context.watch code that's going to actually, as we find out, be responsible for our memory leak. So let's take a look at some Akka.NET source code for just a second here. So looking at dotMemory, we saw the high number. This is the last snapshot we took. We saw the large number of future actorefs, tasks, so forth. One other piece of data we may want to take a look at is, okay, so we found what's being rooted. We know it's these objects. We know it's probably the future actoref, and we think it might be that context.watch that might be doing it. That's one place where someone explicitly, based off our Akka.NET knowledge, retains a reference to an object. Well, the other piece of data we can take a look at, looking at these snapshots, is there a single object that is getting bigger and bigger and bigger the longer it runs? And so we're going to look at this column here, the minimum retained bytes. Let's look up here. We have a runtime method info, whatever, we don't really care about that. But this is interesting. We have a large actor cell, an actor cell that's 450 kilobytes. Actor cells are normally about 1 kilobyte. Having at least one, well, actually, it looks like we have 17 of them, but the fact that some of them are going to be approaching hundreds of kilobytes is an interesting sign here. So if we take a look here, it says they're all 176 bytes, but that's strictly speaking not true. We know that the retained bytes is higher, so there must be an object that's part of the actoref that's bigger. And if you know a little bit about Akka.NET, you're going to immediately recognize that it's probably this guy right here, this dictionary. This dictionary is what we use, and you can take a look at where it's being referenced here. We see it in the actor cell. This dictionary is used for keeping track of those context.watch calls when we're death watching an actor. So we can kind of figure this out by going back to our profile. Let's take a look at the live objects here, and let's look at minimum retained bytes. You don't see a dictionary for iActoref anywhere in here in the first, let's say, several hundred elements that are inside this list. Instead, we have configuration items like HOCON. This is all from Akka.NET's config parsing. But then eventually, as the application runs for longer and longer and longer, in the third snapshot, you'll see that dictionary start to appear as a big item. That probably tells us what is doing the rooting, what is retaining the reference to these objects that are a part of our memory leak. Now the last thing we need to do is figure out, why is it rooting stuff? What's the problem here? This is the ask method in Akka.NET. Now, one of the advantages of working with open source libraries like this is you can just F12 on that method inside the Akka.persistent SQL code or whatever, and it'll go ahead and pull down this source and we can take a look at it. We can see our task completion source being created here. We can see our task being returned down at the bottom. But the real thing we want to take a look at is probably this future actoref. Let's go ahead and dive into this. Implementations. Let's look right in here. Future actoref. So if we take a look down here, you will see that if we receive an iSystem message, which deathwatch messages are, we're going to throw an exception. And that's going to appear on the task. Now, as far as we can tell, inside our running application, we don't see any exceptions occur at all. What this is meant to do is tell the caller that Death Watch will not work. Death Watch will not work on this actor. And it's supposed to blow everything up and kind of communicate it that way. Only one small problem. And this is because I think the original implementer didn't know this. This is kind of an internal implementation detail of Akka.net, which is that this tell internal method, which is basically where actors, this is basically where we typically will enqueue a message in an actor's mailbox. This temporary future actor ref doesn't have one though. It's a single use actor. Well, tell is not where system messages go. System messages are instead handled in a separate method called send system message. So as a result of this bug with this code, we never communicate back to the sender that Death Watch will not work, nor do we ever send the termination message back as well. So as a result of that, that Death Watch collection that this actor, if I go back to my pull request, that this actor is using right here, this collection is going to continue to grow and grow and grow. And that's what we can see when we look at the size of that dictionary rising. So now let's go ahead and really quickly take a look at how we ultimately are going to end up fixing this. So that code we were looking at before was Akka.net 1.537. This is the code from Akka.net 1.538, which we just released yesterday. So if you take a look here, you'll notice that iSystem message handler is gone. Instead, what we have down below is we've overridden the correct method, send system message. And what's going to happen is if we get a watch message, which is what gets sent to us when someone calls context.watch, we will either send back a Death Watch notification immediately if the task is finished, or we will schedule one to run as a continuation task in the future. Either way, we will be able to close the loop back with that original actor now. So whenever this task completes and this actor shuts itself off, it'll get a Death Watch notification, just like if this were a regular, normal, full-fledged actor. And that should cause our memory leak to go away. Okay, so what I'm going to do here to fix this memory leak is I'm just going to go ahead and upgrade from Akka.persistent SQL 1.537 to 1.538. Let's go ahead and do that. And all right, looks like I got to deal with a little bit of DLL hell here. Let me do that real quick. We'll just go to packages.props. Just change that to 1.538, 1.538. All right, compile all of it. All right, good. That should run just fine. Now in .memory, I'm going to go ahead and just configure. Let me just double check this. This should run as a .NET project. Let me just double check it here. Let's see, .NET 9 runtimes. Yeah, it's going to run as a debug mode process in there. Okay, looks like I'm just kind of running the .NET executable directly. You can also configure .memory to go ahead and launch .NET projects and that sort of stuff too. I'm just kind of running it directly as an executable. We should be good to go now. Let's go ahead and run the profiler and see where it takes us. All right, got the application running here. It's not going to log very much. Now, I'm going to take a snapshot right away. Then I'm going to cut, let it run for a little while longer, take another snapshot, then we'll do a comparison. So let's grab our first snapshot here, about 44.4K live objects. Let's see where we're at once the snapshots are a little bit older and we've had more time to run. Okay, so I've actually taken a few snapshots, and you can see here that we started off with a much larger number of objects. This is to be expected when you're first kind of booting a process. And the number of objects has gradually gone down over time, or maybe it's fluctuated a little bit. But our memory is pretty much holding stable. So if we go and take a look at our last snapshot here, and let's look for one of the types we know was leaking before. Task, I guess it was what? Well, let me go ahead and actually just sort this by the number of objects. So we do have some tasks that are running in the background here, but there's like 11 of them, not 1,600. And it's not the type that we were looking at before either. What about future actor ref? Yeah, we see one of these each. So there might have been some that were in flight in the middle of us doing our processing. So we have effectively addressed the memory leak at this point, and it's not going to be an issue any longer. It turns out it was basically just those actors, those future actor refs, not being able to properly signal that they could or could not handle Death Watch correctly. And we ultimately fixed it by just making sure they did implement Death Watch, which would cause their references to be released once the task was completed and the actor was shut down. So just for a little bit of wrap up here, working with dotMemory and trying to diagnose things like memory leaks, it takes a little bit of practice and experience. But the things that we showed you in this video is taking a look at the frequency with which objects are growing. So we did that across multiple snapshots. We also took a look at the size of objects increasing. That's where we figured out where they were being routed. But then the other thing is just kind of thinking about mechanically what causes a memory leak. And the real answer to that is there's a long-lived object retaining references to short-lived objects that should be disposed. That's sort of the heuristic you're going for, and that's why we want to take a look at objects that are growing in size. That's usually one clear indication that we've got, in this case, a collection that's rooting all these shorter-lived objects that should be getting released. So thank you very much for your attention and for following through to the end of this video here. Hope you enjoyed it. Please don't forget to like and subscribe for more high-end .NET content. Thank you very much.